With lesson 33, factors of polynomial functions, graph of polynomial functions. A lot of this goes back to your Algebra 2 pre-cal days, okay? In that a lot of what we're doing, I feel like, reviews, just graphing. I think there's one part at the end that's definitely new, but overall, a lot of review. So, okay, so degree of a polynomial. You guys remember what the degree of a polynomial tells you when you're graphing? Yeah. Remember your degree, okay? It's how many humps, what are humps? What do we mean there? Hills and, what's the opposite of a hill? A hill or I call them valleys. Hills and valleys. But the mathematical word for hills and valleys are mins and maxes. Okay, so the degree of a polynomial, if you recall, it first of all tells you how many possible zeros there are. Because if it's a fifth degree polynomial, there are how many zeros? There are up to 5 zeros. But then in terms of mins and maxes, okay, you can have up to 1 less, so that is 4 in that case. So it's no more than 1 less than the degree. Okay, so that's one thing to remember. Irreducible quadratic factors, such as x squared plus 4, so something like that does not factor, will never cause a polynomial to equal 0. So this means something like x squared plus 4, if it's just x squared plus 4, that graph itself is going to be above the x-axis, never crossing the x-axis. So factors like that can never equal 0. Because if we set this equal to 0 and start solving, you're going to eventually end up taking the square root of a negative. And we all know we can't take the square root of a negative. At least not in reals. Okay? The graph of a polynomial. Okay, guys, do you remember the difference between crossing the x-axis versus touching the x-axis? Do you remember the difference? I just taught this in pre-cal not too long ago. Yeah, it has to do with powers. Okay, so the graph of a polynomial crosses the x-axis when some real linear factor, such as x minus 2, occurs an odd number of times. So if it's x minus 2 the first, the third, the fifth, the seventh, that graph is going to cross through at that point x equals 2. If the graph of a polynomial does not cross the x-axis when a real linear factor occurs, or it does not, when it occurs an even number of times, it just touches it. So if it's already below the x-axis, it comes up, touches it, goes back down. Or vice versa. If it's already above, goes down, touches it, goes back up. Okay, so we're going to talk about that and how that can help us. So as you look at example 1, if f of x, so you have a big long f of x there, yes? Looks kind of ugly. The questions are, at what values of x does the graph of f touch the x-axis, and at what values of x does the graph cross the x-axis? And what is the degree of f of x? Okay, those are your pieces. Got it? So thoughts? Touch, cross, and degree. So, we want to know where it touches the x-axis, crosses the x-axis, and we want to know the degree. Any thoughts here? Nope. No graphing. He says it's going to cross at -4 and 5. How does he know that so easily? Okay. X plus 4 is raised to the power of 1. X minus 5 is raised to the power of 3. So those zeros there are places where it will cross. Does that make sense? So I'm going to cross the x-axis at x equals -4 and x equals 5. Okay. So where am I going to touch the x-axis? He says -2 and 7. Does that make sense? X plus 2 is raised to an even power of 4. X minus 7 is raised to an even power of 2. So we're going to touch the x-axis at -2 and at 7. What about x squared plus 3? No one included that in either group. Yeah. This is an example like x squared plus 4 here. If you put x squared plus 3 and set it equal to 0 and start solving, you're going to end up taking the square root of a negative number. Excuse me. So that represents an imaginary root. Actually, 2 imaginary roots, because it's x squared. Okay? It's not going to force a cross or a touch, though, because it's imaginary. Okay, so that one won't matter. Degree. What is the degree of this overall problem? Huh?
We're just adding all the degrees on the top.
Basically, if we multiplied this all out, which FYI we are not doing, we multiplied this all out, my first term would be x to what power? That's what we're trying to figure out. What? No? X plus 4. What power or what degree does that represent? 1. X plus 2 to the 4th. What's that represent? 4. So there's a 1 and a 4. X squared plus 3. That's an x squared. So that does represent an x to the second. X minus 5 to the 3rd? 3. X minus 7 to the second? 2. Add those all up, and we have a degree of 12. Does everyone see where that came from now? Same thing you've done before, it's just we've got to go back and recall. Okay, and that's being able to answer those questions without looking at your graphing calculator. Being able to, the more details you understand about how these graphs work, the more you can understand about looking at an equation. Okay, example 2. Do not pull a calculator out. Which of the following graphs most resembles the graph of y equals x minus 1 squared, x plus 2 squared?
I agree.
Okay, so question. Jackson?
Yep.
You said it can't, I think it was you, said it can't be A or B.
Yeah.
Why?
Because it goes through and it has even exponents.
Because it what now? Sorry.
It crosses the x-axis even though it has even exponents.
Okay. Not where I was guessing you were going, but yes, that makes sense. I get it. And there's lots of different ways. Okay, so he's noticing A and B has a crossing point. Both of these exponents are even, so these are both touching points, right? Okay. What points do we touch at? 1 and -2. Okay. Now, I'll be honest. I was eliminating A and B for a different reason. What degree is this problem?
That means they're both ends are going in the same direction.
Okay. This is a degree 4 problem, right? Because squared and squared. Even degrees. Do you remember how their end behavior works? Which in Algebra 2, we use the words up and down. But something like x squared, what does an x squared do? It either both ends are going up or both ends are going down. That's true of all even powers. So since this degree is degree 4, both ends have to go up or both ends go down. When do you have a combination of down up or up down? That happens with the odds. Because think about what's x to the third look like. Either starts down and ends up or starts up and ends down. Okay, so for whichever reason you looked, it cannot be A or B. Because it touches at x equals 1 and x equals negative 2, which one did you guys pick? C. And those W's are common x to the 4th shapes. Okay. Okay, questions there? Okay. 33B. Example 3. Again, do not pull out the calculators. And do not type anything in on the calculators is what I'm saying. Which of the following functions is most likely to produce the invisible graph? I forgot that the graph is invisible in your notes. Okay, let me draw in the graph that you're supposed to be looking at. Totally spaced that this isn't in there.
I thought you were being serious,
Is this an imaginary graph? Like
It is imaginary, however, totally spaced that it wasn't in the notes. And then all of a sudden I was like, wait, what? Oh, okay. Okay. Get something like that, you know. Okay, so we are given f of x, g of x, and h of x. Again, we're not plugging these into the calculator and seeing which one looks similar to this. Okay. Based on details of the equation and details of this graph. Which one is most likely to produce this graph? So, give me one of them. I don't want a right answer right now.
It can't be f of x. Or it could be f of x, but it can't be g of x.
Okay, so multiple different reasons here. Okay, so hold your thought, Jackson, because I want to hear it in a moment. Because I think it's probably right too. Okay, I've got two of you. You say it can't be g of x. Why can it not be g of x?
They're both going in different directions.
Okay. As we look at g of x, this is x to the 6th is my highest power, yes? What's that mean about end behavior? What's my graph got to do on the two ends? If it's an even, the highest power is even, my graph does what? Same direction, either up, up, or down, down. The graph in the picture goes opposite directions. Now, curiosity while we're here. Does this graph go up, up, or down, down? G, that is. Why does it go down, down? Because it's a negative out front. Does that sound familiar? The negative lead coefficient is negative. Lead coefficient is the vocabulary you should be looking for there. Okay. So we've declined G. Now, Jackson, you earlier right off the bat said it can't be F. Why did you say it couldn't be F? Okay. So it's not about adding the degrees here. Okay, so let's talk about that. Why last time was it about adding degrees and this time it's not about adding degrees? Okay. But when we look up at example 1 and 2 up above, we added all those degrees to get all those powers to get the overall degree. What was happening with each of those pieces last time? The pieces are all being multiplied. So those are all factors being multiplied. You have to multiply it all out to get your highest degree. Whereas what's different here? It's already multiplied out, and so your highest degree is the term with the highest power. Does that make sense? Good thing to hit on. Okay. So if we talk x to the 7th, that's odd, yes? So what do you know about an odd options? Odd could either be up, down, or down, up. It's opposite directions. What does a positive x to the 7th say? Like a positive x to the 3rd. It starts down and ends up. Is that what we have here? No. So now h of x. What do we have? X to the 5th. What do you know about x to the 5th? It's either down, up, or up, down. What about the negative out front? The negative forces it to start up and end down. Because remember that negative out front flips the graph upside down. Okay. Again, I'm not asking you to draw a graph like that. These are just key features that can help you. Okay. I'm ready to flip the page and talk cubics and quartics when you're ready. Algebra 2 just talked about these, or not Algebra 2, Pre-Cal just talked about these actually. In other words, when I say Pre-Cal just talked about these, I'm saying, oh, it's review for you guys. I hope it's review at least. Okay, and we already kind of talked about a lot about this. So, a cubic function. What's cubic mean to you? 3, good. It's x to the 3rd. Is of the form f of x equals ax cubed plus bx squared plus cx plus d. A cubic function can have either one inflection point only or one inflection point and 2 turning points. Those are your options for what a cubic can look like. Those are the only options. And then it says see pictures below. So we're going to draw those in. Put cubics. What do you know about your basic cubics? What's y equals x cubed look like? Yeah. There we go. Basic cubic looks like such. So this is the option of a cubic that has an inflection point only. Inflection point is where we change. I use the word concavity. I'm not sure you guys know that yet, do you?
Yeah.
What'd you say?
Concavity.
Oh, I think it's
Okay.
I was like, that's my
Yeah.
BFF.
Yeah. One of our big topics before long, we'll be talking about concave up, concave down, which is concavity. But what an inflection point does is my graph turns from being curved down or bold down to being bold up, to where the graph is curved up as opposed to where the graph is curved down. Okay, that's the inflection point. Now, can you guys picture a cubic that has an inflection point and 2 turning points? Yeah, it looks kind of like A and B that we eliminated earlier. Okay, looks something like such. This is a cubic also. Okay, you see it has 2 turning points. Turning points are your mins and maxes. So we turn up here, we turn down here. The inflection point, again, is where it changes from being bold or curved downward to being bold or curved upward. Now, specifically, what do these graphs look like if A is negative? Okay, these are flipped upside down, right? So I'm just going to draw in the basic pictures of really what we just drew. If A is negative, my graph could look like such, or could it have the 2 turning points? My graph could look like such. So those are my options for cubic. Okay, those min and max don't necessarily have to be proportional. They could be, very different. If A is positive, what am I drawing if A is positive? Yeah, basically what I drew up above. Okay, so those are cubics. Good to recognize. Okay, quartic. What do you know quartic? What number? Okay, when you hear quartic, we're thinking 4. It's of the form f of x equals ax to the 4th plus bx cubed plus cx squared plus dx plus e. There are many options for these graphs. See the diagrams below. Okay, so if a is negative, what do you know if a is negative? Okay, it's going to be down, down. Do you remember what the basic x to the 4th looks like? Wider parabola. It has a flatter base. Okay, so one, and I'm going to draw several options in here, but one option is a parabola, but it's a flatter base. I'm not even sure I did that one justice, but now I'm going to go back and forth here. What if A was positive? Instead of being down, down, it would be up, up. Now, if it's just a basic x to the 4th, this is what it's going to look like. If you start throwing in some of those other pieces, the x cubed, the x squared, the x, that's what changes. What can this, what options do these become? W? Yeah. Well, it's not infinite amounts. There can only be, because it's power of 4, that means at most there's 4 zeros and 1 less than that, 3 mins or maxes. So it's not infinite, but as the powers increase, that's when you get more. Okay, so one option is something looking like such. My W can also be lopsided, where I can have one side bigger than the other. I could have one side really small. Okay? Those are all quartic options. Draw whatever variety on your paper makes you happy. If A is positive, the difference is everything opens up, up. Again, they can be lopsided too, depending on what terms there are. I just want you to get the idea that there are a variety. Notice, at most, if it's degree 4, 1 less than that, 3, there are at most 3 extrema, is what we use in the pre-cal. So 3 mins and maxes. Or in other words, 3 turning points. Okay. Technically, a lot of what we just talked about was review. I'm sure you remembered it to varying degrees, but technically it was all review. Now, average value of all the roots. This is probably new. I don't believe we've had this formula or talked about it. Okay. So, the average value of all the roots of a polynomial. So when we talk roots, we're talking like solutions, x-intercepts. And there's a formula here. That x with the line over it is read x bar. Okay, so x bar, which is what represents average value of all the roots, is negative b over na. Now, a and b will come from the polynomial. So like a is always your leading coefficient, so that's always your number in front of the highest degree, highest coefficient, or highest power. Sorry. B is always the next highest. Okay? And then n, notice it's written in here, n is the biggest power. So whatever that highest degree is there. So notice what it says right here. In a quadratic, x bar is the x value of the vertex. So if you find the average value of all the roots, well, in a quadratic, there's 2 roots. And so it's just the vertex, which is the center. In a cubic, x bar is going to be the x value of the inflection point. So that center point, okay, notice a vertex is the center of a quadratic. The inflection point is the center of a cubic. And then in a quartic, which remember quartic is degree 4, x gives us a good idea of the center of the graph. And again, because it can be lopsided stuff, there's not a specific place it gives us, but it gives us a good idea of the center. If it's just one of those quartics that looks a lot like a parabola, then it's going to give you the vertex. But if it's one of the W ones, it kind of depends on what it looks like. So let's use example 4 to practice. Example 4 asks us to sketch the graph by hand. So this is not grab your calculator and sketch it. This is what things can we glean basically off of everything we've talked about today. What are the details that we know for sure out of this graph?
If you know a negative, you're going to go negative. It's going to be going from top to bottom. As odds.
Okay.
-3.
So right here, several of you guys have already picked up on this stuff, right? The negative, upside down, the 3. What's that power of 3 mean? It's either down, up, or up, down. Because it's negative, it's going to be start up and end down, yes? Okay. What kind of graph is this overall that I'm sketching? Okay, because it's an cubic. Now, one of the things I do want to find, because it's a cubic, obviously we were just given a formula, right? Because it's a cubic, what can this formula find? The average value of all the roots, what is it in the cubic? Inflection point. So that's something we can find. Now, in order to use that formula, we need to know n. N is the biggest power. What is the biggest power in a cubic? 3. Let's go ahead and talk about our ABCs. What is A? -1, because it's the coefficient of the highest degree power. What is B? 3, because it's the coefficient of the next one. C? -2. D? 3. And there is nothing past D on a cubic. Okay. So in order to do x bar, it's -b over NA. So, what you got for me? Okay, -3 over 3 times -1. -3 over -3, which is 1. What is that 1? Okay. The x value of my inflection point. So I know when I go to draw my graph, I have an inflection point at 1, something. So the x value is partially handy. How can I find the whole inflection point once I know the x value? Do what? Plug it in where? Okay, so if we know x is the first part of the inflection point, do we have an equation here? Yeah, plug it in to your original equation. And so y equals, it's -x cubed, so that's the negative of 1 cubed plus 3 times 1 squared minus 2 times 1 plus 3. Becomes -1 plus 3 minus 2 plus 3. So what is my inflection point now? 1, 3. Okay, let's see. There's probably one other easy thing that we can tell just by looking at our graph or at our equation. You guys remember how to find a y-intercept? Officially, the rule is if to find a y, the y-intercept is wherever x equals 0. So officially, you can put 0 in for x. Well, you put 0 in for x, what remains here? 3. Okay. Your y-intercept, if you have a constant, your y-intercept is always just the constant. So my y-intercept is going to be 3, or in other words, the ordered pair 0, 3. Okay. I think I'm about ready to sketch this graph. Inflection point is the point on an x cube, like, our typical x cube is at 0, 0.
Yeah.
So, like, the inflection point on a typical x cubed graph is right here. Okay? It's that point where right here, I don't know if you guys can tell, right here my graph is kind of curved facing downward. Whereas right here my graph is, like Jack said something earlier about being parabola. This is kind of part of the upwards parabola. This is part of a downwards parabola. Okay? We'll talk a lot that an inflection point is where your concavity changes, where you change from concave up to concave down. We're not quite there yet, but okay. What do we got here? Do we know enough?
Yeah.
We know we have to go through the point 0, 3 and 1, 3. And what do we know about end behavior? If I sketch it in pencil, my end behavior, we start up and end down. Thoughts on what my graph is doing here? Okay, how do we go through those middle 2 points, though? Yeah, it doesn't go real flat, though.
It's gonna be.
Yeah. Now, keep in mind, this is my inflection point, yes? Okay, so if that's the inflection point, so kind of, forget this one. An inflection point, we start up and end down. What are my options? My graph could look like this, right? There's my inflection point. Could I have a point that is right here and still in that graph? No, so what's the next option? Where's my inflection point on this one? There's my inflection point, commonly referred to as our IP. Okay, if that's our inflection point, where is, and that's 1, 3, where is 0, 3? 0, 3 is just that random point there. Okay, that's what you're drawing. Easier said than done, I know. So I'm going to go down through 0, 3. I have to have a minimum between 0, 3 and 1, 3. Come back up and go down something like that. Like where you end up crossing the x-axis and stuff? No, because we didn't find that information. The graph's not the greatest there, but it gets the idea. Okay. Okay, guys. Use a little bit of work time here. Lesson 33.